Okay, so so I'm going to talk about drought and soil moisture and tree stand vulnerability to drought. And just a few things to start off. I'm a climate fellow, part of the Northwest Climate Science Center, so that's kind of where my base is at. And also, I want to mention this is ecological adaptation session, but I'm a hydrologist, eco-hydrologist technically. So I like to communicate with ecologists, but you'll definitely see that come out in the presentation. But I like obviously interacting with ecologists. That's kind of where the rubber meets the road. And third of all, too, I just want to mention that I'm a third of the way through the fellowship. I kind of have a truncated fellowship, and I'm only about a third of the way through. So this is preliminary, so bear with me with that preliminary results. So to start off, the Northwest is a very diverse place, and it's areas we like to hike in, hunt in, but they're very diverse, whether you have a mixed conifer stand that's pretty wet, or a very dry ponderosa pine stand that's mixed with sagebrush. So very diverse ecosystems we live in. And because it's so mountainous, you have steep biophysical gradients. So you can go 10 miles and you go from pretty different temperature regimes, pretty different precipitation regimes. So it's really a challenge for managers. You can be in the Umatilla National Forest or the up here in the Idaho Panhandle National Forest, and you can go from mixed conifer to ponderosa pine. And so it's challenging when you have these diverse ecosystems. How do you manage those? And on top of that, you have climate change, which is what this conference is about. So this is a figure I think I've seen once, but I really like it because it's with measured data. It's Reynolds Creek Experimental Watershed, and they basically have measured how the upper part of the catchment has been mostly snow, and then since they started in 1968 until 2006, that area is really diminished. So it's seeing these big impacts we've been talking about with climate change. So as a manager, you have these steep biophysical gradients. And on top of that, you have climate change happening. So it's kind of like a game of 3D chess. Like, it's a really tricky thing to think about and know what to do. And one of the main tools that's also been talked about here is how to manage these forests is thinning. That's something that was talked about the plenary session yesterday quite a bit. And there's a need with limited budgets to prioritize. Where do you thin? Do you thin higher in the watershed or lower? And in just thinking about this, and you often hear talking about, since in the Northwest, ecosystems are driven by precipitation, you usually think, well, maybe a drier site would be more vulnerable, and that would be, where you need to thin, potentially. But looking at some data, this is out of Reynolds Creek, a paper a few years ago, and looking at, this is May 1, SWE, which is snow water equivalent, so just snowpack. And you can see that high elevation hasn't been much change in snowpack on May 1st. Mid elevations, there has been quite a bit of change, whereas lower, and not even extremely low, but lower elevation, not much change in snowpack. So although you might think, well, maybe lower elevations would be more vulnerable to drought because they're drier, maybe they are experiencing shifts that aren't going to be as impactful. So again, it's really tricky for managers to think, where, if we're going to use this tool of thinning, where do we use the tool? And so, don't need to know all this, but basically this is kind of a way that Andrew et al. Kind of looked at soil moisture, drought vulnerability, tree drought vulnerability, and so a lot of factors, but we're really going to focus in on soil moisture. So the objectives of this work are principally first, which tree strands are most vulnerable to drought, and then can forest thinning reduce drought vulnerability? So as I mentioned, I'm in the beginning of this project, and so going to be principally focusing on objective 1, just which tree stands are most vulnerable to drought in a watershed. Okay, so before I start kind of my methods section, is just want to mention some collaborations. And I meant to point out originally, and you'll find out, I'm collaborating with a couple different groups. But one of the main collaborations with Ben Soderquist, which is Ben here. Ben is not here. I can make fun of him. It's great. Anyway, so Ben's one of the main collaborators. He's one of Tim Link's students, and so we're working together. And again, part of the main work is to look at drought vulnerability, and that's probably what he's doing too. But we've kind of been collaborating together, as they'll kind of come out in the rest of the presentation how we're working together. But just wanted to mention that at the outset. So you have these steep biophysical gradients, and you have managers, and you're thinking about where to thin. It's there's a lot to think about, and there's a need for really fine temporal and spatial resolution data, and so that's one aspect. And then two, just look at across diverse forests. So again, if you're in the Umatilla National Forest, for example, you're going to have ponderosa pine in lower elevation and more mixed conifer high elevation. So you got to think about these kind of dry versus wet ecosystems. And so 2 sites, we wanted to do some simulations at 2 contrasting sites. We call them 2 end-member sites. So 2 great sites for that are H.J. Andrews on the left, and then Reynolds Creek Experimental Watershed on the right. And I'll talk a bit more about them. In general, H.J. Andrews is mostly a mixed conifer site. You have cedars and Douglas fir, very wet because it's on the coastal range. And then Reynolds Creek is a semi-arid watershed. The pockets of aspen, which we'll be looking at, there's pockets of it that are usually occur downslope of drifts, snow drifts. And so there's some similarities between these sites. They're both in general Mediterranean, so they get most of their precip in the winter and less precip in the summer. They're both have about an 800-meter elevation contrast, so they're similar in that way. And then they both have long-term data sets, which is great for the kind of work, the kind of simulations we want to do. So, but they were different in that mainly they had H.J. Andrews much more precip, Reynolds Creek much less precip, so it was a good contrast there. And then also the vegetation's different, as you'll see. So just a brief overview of H.J. Andrews. Again, about an 800-meter elevation span, and so we're looking at 3 sites. We're looking at they call it the primary or PrimeNet meteorological site, which I'll abbreviate as PRE throughout this presentation, which gets 2,200 millimeters or 87 inches. I want to kind of do the metric English, put both up there. And then the center meteorological station, which is gets a little more precip, 2,500 millimeters, so a little bit wetter. And then also the upper lookout site, which gets a little bit more precip, but not a huge precipitation gradient, pretty wet across the whole watershed. And then Reynolds Creek Experimental Watershed, which is also a CZO, recently funded. We're looking at 3 sites as well across the elevational gradient, except there's a bigger precip contrast. You have Upper Sheep, which is 425 millimeters or 17 inches of rain. And then at the top is Reynolds Mountain East, which gets about 1,100 millimeters or 43 inches, so quite a bit more rain. So quite a bit larger precipitation contrast in the coastal range in H.J. Andrews. And then our middle elevation will be Johnson Drought, which gets about 680 millimeters of precip. Okay, so we want to look at current and then future vulnerability to drought. And so for our future climate projections, we're using the MACA data set. We use 20 GCMs. And here's just max air temperature, but what we did is we took, we used the RCP 8.5 scenario for the mid-century, so just about 50 years in the future, a little less than 50 years. And we basically took the average max and min temperature, how that's changing from current to future per month, and then so we took the historical data and then increased that with that average monthly temperature. But this is just showing the max temperature. I just want to show kind of how it differs between H.J. Andrews and Reynolds Creek. And so we can see here that Reynolds Creek, again, this is just annual max temperature, warms about 2.9 degrees centigrade. Reynolds Creek is warming, projected to warm a little bit more, upwards of 3.4 centigrade. So that's one difference between the 2 watersheds in the future, potentially. So when modelers, ecosystem modelers, especially are often looking at this, they use certain models, and one of the main ones is Biome BGC, which is also used in RESIS too, if anyone's familiar with that. And so Biome BGC is really good at nutrient cycling. It's good at incorporating CO2 dynamics, but it has just one soil layer, as you can see here, so it's not as good as a soil hydrology aspect. And so you can see here is at one of the sites things is at Johnson Drought. So the black is the measured data, and then the dotted blue line is the simulated. And you can see it really misses that steep summer dry down as it goes into June and July. So it doesn't quite capture that. And that's really important because the sooner the soil moisture draws down, the sooner the tree experiences drought vulnerability. So if it's not simulating the summer dry down very, very well, that's going to be an issue for modeling drought into the future. So Gerald Fleshinger to the rescue. That's Gerald. He's a collaborator, member of the Northwest Watershed Research Center. And he developed the Simultaneous Heat and Water Model, or SHA for short. And this model is really good at simulating some of these fine-scale processes. And so it's basically a one-dimensional model. It's a bunch of nodes that are connected to each other, and the heat and water can go between those nodes. So you have the canopy, snowpack, litter, soil, and you can have as many soil nodes as you want. We had 16 soil nodes, and then it's forced with hourly precip, wind, air temperature, relative humidity, and soil radiation data. So it's pretty fine temporal scale, relatively. And then, yeah, 16 soil moisture nodes. So again, instead of BioBGC, which is just one, it's 16 and down to 4.5 meters. So you have more at the top, and then it gets greater spacing as you get down. And then also for data at those H.G. Andrews and Reynolds Creek, in addition to those hourly climate data, there's soil moisture data to validate the model. So one of some of the things we're going to be looking at, so with looking at drought vulnerability in aspen at Reynolds Creek, and then conifers at H.G. Andrews, we're going to change height. So aspen shorter, 4.5 meters compared to conifers. LAI is much smaller in aspen than conifers. And then rooting depth is shallower at 2 meters compared to 3.5 in conifers. So those are some of the different parameters. Okay, so as I mentioned, so BioBGC does a lot of things great. Nutrient cycling does great, but not quite soil moisture. So how does SHA do? It does quite a bit well. This is before the project started. You can see that it follows that early summer dry down that happens especially in the semi-arid areas. So that's what we're looking for, because we want to look at soil moisture and drought vulnerability. So some of the scenarios we'll be looking at. So we'll take, again, current measured data at each site that started, the site started anywhere from 2003 to 2007 and then all the way to 2014. And then for future temperature, as I mentioned, RCP 8.5, mid-21st century. And then just to be able to compare the two, we just took the current data and increased the temperature on a monthly basis. So if from the current to future is, again, like 3.1 centigrade, for June, let's say, then all the June data is increased by 3.1 degrees centigrade. So just to kind of have a direct comparison. And obviously, precip is potentially going to change, but as we've talked about today, that's highly uncertain, so we didn't want to really touch the precip at this point. And then, I should mention too, so the scenarios will be, so we'll have current and future simulations, then we'll have trees, so aspen or conifer, then thinned, which again, I'm not going to talk about today, but also shrub, which is sagebrush in Reynolds Creek, and then just like snowberry shrub in H.G. Andrews, and then no vegetation. So we kind of have 8 scenarios for each watershed. And then how we're going to look at drought vulnerability, look at plant wilting point. So in both when it occurs and also how long plant wilting point occurs. So, and I'll talk a bit about plant wilting point in a sec. So just before I kind of launch into the main results, I just want to look at model validation for our model runs. And so this is CenMet at H.G. Andrews at 100 centimeters water content. And so we can see, and to be honest, even as a modeler, this is surprising how well the model agreement with measured. So you can see measured in the solid line and modeled in the dotted line. And it follows pretty well with the measured data, which is pretty, again, I was almost surprised that it followed it that well. So, which is really what we're looking for, because again, with drought vulnerability, you're concerned at when a tree experiences low soil moisture and for how long. So the fact that it follows it that closely is really good. So first, before I launch into these graphs, these are all metric potential. I'm going to define that because, again, as a hydrologist, it's kind of my bread and butter. So this is basically suction that the soil exerts. And so when it's close to FC or field capacity, it's a pretty not tightly held water, whereas the lower you get, the more tightly the water is held, so the soil is kind of pulling at the water more. So basically below what we call usually about negative 150 meters is below. That's a plant wilting point is usually what most studies say. So basically below this, the tree loses. If it's a tug of war, the tree's winning here, and then when it gets below that, the tree loses the tug of war of over the water. So just to keep that in mind. And so this is at Reynolds Mountain East, looking at 20 centimeters, different vegetation. So we can see that aspen compared to the shrub, mountain sage, no vegetation. Aspen, because it's much deeper rooting depth, you get much greater negative matric potentials. And I'm actually not going to show shrub or no veg for the rest of the presentation, just because aspen clearly, that's what exerts, you get the most negative matric potentials. So, and then for this, again, for the current climate, you see 1 year in 2013 that it did kind of dip below that point of plant wilting point, but just briefly. So now again, we want to look at across the watershed. What do we see? And so blue is Reynolds Mountain East, so it's high, and then green is Johnson Drought, so middle elevation, and then red is Upper Sheep Creek, which is lower elevation. And so we see what we expect to see again. Upper Sheep Creek, the red is drier, so you see a lot more time spent in and below the plant wilting point. And we even see these midwinter dips, which is, again, it's kind of preliminary. I kind of want to look at what's going on if the soil is bare and you have, even in the middle of the winter, water being lost from the soil. I'm actually not sure if that's what's going on, but obviously drier sites experience a lot more negative water potential. And then at H.G. Andrews, as you might expect, doesn't experience much soil moisture drought over the measured period. So again, plant wilting points all the way at the bottom of the plot. Across all three, the higher, middle, and lower elevation don't really see much. You're really getting close to plant wilting point. So you do see a little bit. The soil gets a little bit more negative in the lower and middle elevation, but that's really it. So not much to. Okay, yeah, I zoomed in a little bit. So anyway, you do see at the so upper lookout site, the soil moisture doesn't get quite as dry as the other two sites, but in general, they don't really get close to experiencing really the plant wilting point. Okay, so now we want to kind of look at the future simulations and what's going on. So just to walk you through the same y-axis as we've been looking at, but the solid line is the current climate, and then dotted line is the mid-21st century. And so a couple things we notice. First, at the Upper Sheep, the drier site, you see that time that it experiences in soil moisture drought is increasing. You see that kind of widening. You can also notice that for the Reynolds Mountain East, the higher elevation site, you can see that some of the wetter years, the years that didn't experience soil drought as much, didn't go into soil moisture drought. So 2011, under the future warming, still isn't experiencing soil moisture drought. Although in 2012, you see quite a bit of increase in timing of under soil moisture drought. So you would see an impact at the higher elevation there. And then looking at H.G. Andrews, again, even under RCP 8.5, mid-21st century. Is that how much time I have? So 1 minute of questions? Okay. Okay, let me, I see I'm getting short on time. Anyway, so yeah, H.G. Andrews didn't experience, even under that future climate, didn't really experience soil moisture drought. And so, although there was interesting, there was a shift from, at the upper lookout site, it did become more like the middle site, which could be due to less snowpack potentially. I'm actually going to go and let's get a shot. That was from another site. I'll skip future directions. There's quite a few future directions I'm going to touch on, but I won't touch on that now. Just want to say thanks for your time, and maybe I'll take a short question if there's. You can do one. Yeah, one question. So anyway, thanks. No, that's fine. That's fine.
Future directions?
Pardon me?
What are your future directions?
Sure. Yeah. So did anybody see Ben Soderquist's talk? Nobody? A couple people. So what he talked about, and what's a big factor in Reynolds Creek is drifts. So I'm going to incorporate drift factors. I didn't get a chance to do that. So, because there's drifts usually uphill of those aspens, so they add quite a bit of moisture. But I actually don't think it'll be that big of an effect because you're going to experience the dry down regardless of the drifts, so that's an issue. Future, I need to, so I didn't mention, but for these future climate, I only did annual increases. So I just said, what's the annual increase? It's like 3.2 degrees Celsius, but I do monthly. And I might incorporate temperature variability from MACA. Need to do undergrowth simulations. Need to actually do the thinning simulations. That's one of the main, deliverables to managers. Look at actually how thinned stands will be more resilient potentially. Do sensitivity analysis, especially the vegetation parameters of rooting depth, LAI, that sort of thing. And then also one of the main goals too is what I have a picture of Ben here is help. So we have measured soil moisture data to validate our runs, both for his biome BGC and mine, but obviously don't have it for the future. So have my model runs help inform his for biome BGC. So anyway, thanks.